And welcome back to Calculus 2. We're going to continue our discussion of differential equations, and this time we're going to be talking about Euler's method, named, of course, after the mathematician Leonhard Euler. It is a strange way of spelling it, but then, spelling is weird, guys. I went to the National Spelling Bee in 1998, and I can tell you from an expert, spelling is weird. So in this one, Euler's method is a method for approximating the solution of a differential equation, which, remember, is a function. It works by generating a sequence of approximate y values. And what we're basically going to do is we're going to start from a point, and then we're going to move off of that point to approximate the rest of the function. The further we get out from our exact point on the function, really the more error we're going to have, but it's just used to approximate. So let's look at how we're going to do this. We're going to use the linearization of a function using its first derivative. And our problem we're going to work on is going to be 9.1, problem 14. And it is on page 543. The instruction is use Euler's method to calculate the first three approximations to the given initial value problem. So use Euler's method to calculate the first three approximations. To the initial value problem below. So the initial value problem is y prime. There's some additional instructions as well. They want us to calculate the exact solution and look at how accurate our approximations are. But we'll work from there. Y prime equals y squared times 1 plus 2x. Then we have y of negative 1 equals 1. And they gave us a dx as well. Dx is where they want us to go with the approximations, because they gave us an exact point. This is an exact point. So what we're going to do now is we're actually going to move from that point over and look at, well, if we go 0.5 to the right, that would be negative 0.5. What will the approximation say it's then? And then we'll compare that with what the actual function would say as well. And then, the next one on from negative 0.5 would be at 0. So we'd look at that. The next one on from 0 would be positive 0.5, and we look at that. So let's see here. The linearization of a function, L of x, is approximating y. Linearization of y is it is the point slope equation, so it's the y value, so y sub 0 plus the derivative there times the difference in x values. That was basically the formula for the tangent line of a function, or the linearization as we called it back in chapter, I want to say 3. In this case, though, we're going to calculate subsequent approximations. So our first approximation, we're going to take our point, our x1, y1 here. We're going to take our initial point, our y sub 0, and then we're going to add dy dx, so that is actually just our differential function here, our f prime of x, y, and we're plugging in our point times x minus x naught. So, and this will be our next point we're looking at. So then our second approximation would be, y1 plus f prime of x1, y1. times x2 minus x naught. And this is always just going to be 0.5, so there's not a whole lot to do there. So in general, our format is going to be y sub n equals, because, you know, our dx is 0.5, that's constant, we're always doing that. Our y sub n is just going to be our previous n, so our n minus 1, plus f prime, so our derivative, xy. So x sub, let's see, n minus 1, y sub n minus 1. I really should have done n plus 1. That would have made for a simpler notation. I'll change that around. Okay. So this becomes x sub n, y sub n, and then times our delta x, or dx. That's going to be our formula. That'll get us subsequent approximations. And this is Euler's method. You evaluate at each point which direction you're going based on the derivative, and then just find it. So, let's start off. Our initial point is -1, 1. So, our y sub 1 is going to be our initial y value, which is 1, plus our derivative, which, let's see, plug in here. 1 squared is 1, because we're plugging in y. Plugging in x is -1, so 1 plus -2, so that's -1. 1 times -1 is -1. So 1 plus -1 times 0.5. So that's going to be 1 minus 0.5, so that is 0.5. So that's our second point. Our second point would be negative 0.5, positive 0.5. Our y sub 2 would now be our y value, so 0.5. And then our new derivative. So this I might start bringing up the calculator here in a bit, because we'd have to do 0.5 squared times 1 plus 2 times 0.5. Or is that negative? It's negative 0.5. Negative 0.5. So that is 0.25 times 1. Isn't that 0? 1 minus... Yeah, 1 minus 1. Okay, 0. That's easy. That's 0. Which means this is plus 0 times, it doesn't matter what it's times, but it's 0.5. So it's still 0.5. Alright, but remember, now our point is going to be at 0, 0.5, because we're still advancing our x values. So our third approximation, our last approximation. Our last approximation would still have 0.5 here. But now we got plus. Let's see, what's our derivative going to be? Well, this should be easier to plug in. Plug in 0.5. You got 0.5 squared times 1 plus 0. So that is going to be 0.25. And we come up with 0.25 times 0.5. Okay, so that's 0.5 plus, let's see, half of 0.25 is 0.125, so that is 0.625. So that's our second, well, I missed my decimal point, and our first approximations, 0.5, 0.5, 0.625. So those are approximations. Let's now see if we can solve this differential equation. That's dy dx. This doesn't look too hard to separate variables. Honestly, I can just divide the y squared off, multiply the dx. So 1 over y squared dy equals 1 plus 2x dx. Integrate this side. that is y to the negative 2. So increase by 1 to get y to the negative 1. So negative 1 over y equals x plus x squared plus c. So I guess solving for y then, I'd flip both sides, move a negative over, so y is negative 1 over x squared plus x plus c. And I got an exact value, so if I plug in negative 1, y of negative 1 equals negative 1 over negative 1 squared is 1 minus 1 plus c. This should all equal 1. So I just get negative 1 over c equals 1. So flip this side, multiply by negative, c is going to be negative 1. So our exact answer is y equals negative 1 over x squared plus x minus 1. Now let's actually compare those values. So if I plug in negative 0.5, right? So these are the approximations. The actual real y1 would be negative 1 over 0.25 plus minus 0.5 minus 1, which is negative 1 over, it's 0.25 minus 1.5, so it's negative 1.25, which is 5/4, so it's 4/5. So I get 0.8 on that one. y2 if I plug in 0, that should be even easier. 0, I just get negative 1 over negative 1 is 1. If I plug in y3, let's see, that we plugged in 0.5, positive 0.5, yeah. 0.5, 0.625 would be that. So then we would get, plug in positive 0.5, you get negative 1 over 0.25 plus 0.5 minus 1, which would be negative 1 over negative 0.25. Is that right? Yeah, which is positive 4. So it's increasing again. I just paused my own video for a second to go check the solutions, and that's correct. The last approximation comes out to be 4. They did actually tell us in the problem in the book to round your answer to 4 decimal places. We did never actually get out to 4 decimal places, so there wasn't any need. But yeah, there you go. So between vector fields and Euler's method, that's all a 9-1. It's just kind of a lead-in to other problems we'll be dealing with. Next time, we'll be looking at first-order linear differential equations. Those are equations we haven't really talked about how to solve yet. We've talked about easily separable equations before. Linear equations are still separable, but they're a little bit harder to deal with. So we'll look at the methods for solving them in the next section. And we'll probably spend, I think we may end up spending 3 videos on that section, because the initial work of it is going to take some time. Doing straight problems is going to take some time, and then doing some applications. We might fit it into 2, but we'll see. That'll be it for 9-1. Have a great life.